Doctor must die!
I should hold it. They followed me. How's that possible? Oh, what do we have here then? Hello there. I'm sorry, I may have brought with me... Sorry. Your video-y person will be here soon. He's just... Come to think of it, he's outside. Excuse me. The idea of travelling through time has a lot of appeal, whether it's Marty McFly going back to 1955 or Bill and Ted's Excellent Adventure. And what sci-fi nerd hasn't imagined what it would be like to be a companion of the Doctor, travelling through time and space and saving the world for good measure? But is time travel really possible? If we had the right technology, the right know-how, could we build a TARDIS? Could we build a time machine? It turns out that as much as we like to think that the passage of time is constant, it's actually not. Turns out time is... relative. Okay, so let's get right down to the question. Is time travel possible? Yes. In fact, you are traveling through time right now. No, you are. Right this second, you are traveling through time. When you started watching this video, you are further back in time than you are right now. So it follows that you have been traveling through time. In physics, there aren't just spatial dimensions, there's also a time dimension. If I walk forwards, I'm walking forwards in this spatial dimension, but I'm also walking forwards through time. As long as a single particle in my body is moving, as long as it's interacting with the fields around it, I am moving forwards in time. Okay, but that's a cop-out. That's not what we mean when we say time travel. Okay, so what do we mean? We mean, can we move in time relative to other people? Can we move forwards or back in time, all the while our friends and family continue as normal? To figure this out, we have to ask Einstein. He was a really smart guy, but more than that, he was famous for formalizing the theories of special and general relativity, and that's what's going to help us answer this question. The principle of relativity, the principle that underlines all of relativity, says that there are different reference frames and that the laws of physics have to hold in each of them. You might have two reference frames where one person sees one thing and another person sees another thing, and they seem to contradict, but both are equally valid, and in both frames the laws of physics have to hold. So let's say that we have a really fast spaceship. Here's our spaceship. And remember that spaceships don't need to be aerodynamic, because there's no air in space. So a spaceship shaped like a brick makes just as much sense as any other shape. And now let's take a set of identical twins, Lucy and Laura, born moments apart. And let's put Lucy on the spaceship. Now let's also say that on the back of this spaceship there are two mirrors and a laser. The laser beam sends laser light towards one of the mirrors, it bounces back to the other mirror and goes back and forth bouncing between the mirrors. Now we know what the speed of light is. It's 300 million meters per second. So we can calculate how long it takes to go from one mirror to the other. So Lucy, looking at her little mirror experiment, will see that the light travels a distance d in a time t, and speed is distance divided by time, so the speed of light here is going to be equal to the distance between the two mirrors divided by the time it takes for the light to travel from one mirror to the other. Just speed is distance divided by time. Pretty simple. But now let's think about what Laura sees watching the spaceship from the Earth. Let's say this setup is on the back of the spaceship and Laura is watching it through a telescope. Now Laura is watching the laser beam too, but what she sees is quite different. She sees the laser beam move from mirror to mirror too, but from her point of view the spaceship is also moving to the right. If that movement is fast enough, if it's comparable to the speed of light, by the time the light gets from one mirror to the other, the whole ship has moved to the right, which means each little photon that makes up the light has moved not just to the top mirror, but also to the right. And the same thing on the way back down. As the light moves back down to the bottom mirror, it's also going to move to the right. So from Laura's point of view, the beam of light is making a zigzag shape, like this. So Laura sees the light travel a different distance, which we can call d2. And just from basic rules of triangles, this distance is always going to be at least a little bit longer than the distance between the two mirrors. So Laura sees that the light travels a greater distance. But the speed of light is an important constant in the universe. The speed of light can't change, it doesn't change. And because of the principle of relativity, it has to be the same no matter your point of view, no matter your frame of reference. So Laura's speed equals distance over time equation looks different. The speed of light c has to stay the same, but now we have a bigger distance d2. So for this equation to work, you would also have to have a longer time, t2. For example, if you have a fraction, say 3/4, and you increase the 3 to 6, the only way it's the same fraction is if you also increase the 4 to 8. 3/4 is the same as 6/8. So from Laura's point of view, the light has travelled further, which means that the time it took to travel between the mirrors was greater. So from Laura's point of view on the Earth, more time has passed than from Lucy's point of view on the spaceship. Laura back on Earth has experienced more time than Lucy. So when Lucy comes back to Earth, Laura will be older than her. And if the spaceship was travelling fast enough, a great enough proportion of the speed of light, and if it travelled that speed for long enough, she could come back and years could have passed. So in this scenario, Lucy has travelled forwards in time. Now this might seem like some kind of trick. Surely time can't pass at different rates for different people. Light must just be able to travel faster than we think. But we can actually test this. In order to travel significantly forwards in time, like a matter of years, we would have to have a spaceship that went a significant proportion of the speed of light. It would have to go super fast. We don't currently have any spaceships that can go that fast, and the energy required to do something like that would be huge. But in 1971, we took two extremely accurate atomic clocks. We synchronized the two clocks so that they were perfectly aligned with each other, and we left one of the clocks on the ground while the other one went on a supersonic jet. The clock on the plane went flying around for a while, and then the plane landed, and the clocks were brought back together again. When the plane returned to the ground, the clocks were no longer synchronized. The one that had been on the jet had moved into the future. Not by a lot, only a fraction of a second, but it was measurable and it fit perfectly with Einstein's equations. So it turns out that time isn't the constant it seems to be. The speed of light in a vacuum is the constant, and the flow of time changes according to your point of view. In this case, according to how fast you're going. So can you move forwards in time? Yes, you just have to build a really fast spaceship. Can you build a TARDIS or a DeLorean? Probably not. Travelling forwards in time is relatively easy. Relatively. Backwards in time, not so much. That's just not possible. Oh yes it is. Oh no it isn't. Doctor? Oh yes it is. Hey, what is this, a pantomime? I'm having flashbacks from the time that I landed right in the middle of Jack and the Beanstalk. Look, people think that time is a strict progression from cause to effect, when actually, in a non-linear, non-subjective sense, it's more like a big ball of wibbly-wobbly, timey-wimey stuff. To quote you, what? Yeah, I don't know why, that explanation always seems to get away from me. So it's also kind of like a ball of string. All you have to do is push two strings together and jump across. Wait, hold on. Are you talking about wormholes? Wormholes. That's brilliant. Yeah, close enough. So the time vortex is kind of like a wormhole, except the TARDIS would be the hole and the vortex would be the worm. Okay. Well, actually, I was going to talk about wormholes. So usually, the only way an object could be seen as going backwards in time would be if it was going faster than the speed of light. This interpretation is kind of controversial, but even if that were true, the laws of physics tell us that to travel faster than the speed of light is impossible. To speed up above the speed of light, you would have to supply yourself with infinite energy. But as the Doctor mentioned, I think, maybe we could go through a black hole instead. Some physicists have theorized that maybe, under ideal conditions, a black hole could be a pathway to another part of space, and maybe even to another point in time. Under those circumstances, they're called wormholes. But to fly into a black hole would surely mean that you and your spaceship would be crushed into an infinitesimal size and form part of the black hole. At best, bits of you could end up somewhere. So perhaps building a proper time machine isn't possible, unless you happen to be Gallifreyan. But travelling forwards in time certainly is. You would just never be able to come back. A non-profit organization called the Mars One Foundation last year asked for volunteers for a one-way mission to Mars, a mission with no hope of ever returning. 200,000 people responded. How many people do you suppose will volunteer for a one-way trip to the future? Would you? Let me know in the comments, and as always, keep questioning. Thanks for watching. If you like this video, feel free to share it, like and subscribe. But most of all, if you do nothing else, please leave a comment below with your questions, thoughts and suggestions. They really are appreciated. Until next time.
To your stations, we're under attack. Roll out the cannons. Return fire.
Keys in the car, my heart in the boot. I was waiting and pacing up and down on the streets with my hands in my pockets.
Heave! 2-6, heave! 2-6, heave!